Welcome back, students. We went through a power series method around an ordinary point. What do you mean by the ordinary point? A point where everything, all the coefficient function, everything is analytic. Now let's consider a power series expansion method around a singular point, but not every singular point, a regular singular point, some easier type of singular point. What do you mean by that? It's a singular point, so not everything here is analytic, which means you may have some singular point like denominator 0 or things like that. But here's a condition. Appropriate multiplication of certain power will yield an analytic function. This definition is really hard to follow, so let's go through with that with an example. Okay, here we go. Let's prove that this ordinary differential equation has a regular singular point at t equal to 0. Okay, if I divide everything by t squared will go down to denominator, so we're going to have a problem. Coefficient function will not be analytic anymore at t equal to 0. But t squared, second power, first power, so if I multiply t squared, let's see, n minus k power. So if I multiply 2 minus 1 power over 2 minus 2 power, then analytic. So second power, first power, 0 power. If we could go backward like this, then that's a regular singular point. You see? This is second derivative, first derivative, 0 derivative. But look at the denominator. Let me expand the font. You have denominator, it's hard to see. Second derivative, first derivative, 0 derivative. But if you look at denominator, it's backward. Second power, first power, 0 power. Okay? That's an indication of regular singular point. Another example, I think this is a non-example. Yeah, here we go. We have two singularities here. If I divide everything by t squared minus 4 squared, we get this expression. Okay, just an algebra, right? And then you can factor the denominator. So what do you have? You have t plus 2 and t minus 2. Both can become 0, so at t minus 2 equal to 0, at that point we have a singular point, t equals to 2, which comes from this factor. And then t equals to negative 2, which comes from this factor that can turn 0 in denominator, so that no longer analytic. And then that 2. So we have those two singular points. T equals to negative 1, t equals to 2 and t equals to negative 2, blue and red respectively. But after simplification of this 2 and then that, we have first power there, second power there. Let's look at it again. Second derivative, first derivative, 0 derivative. Look at the denominator. 0 power, first power, second power. Backward. So that's regular. Blue is regular. Regular singular points. Kind of sound like an oxymoron. How about red? Second power, another second power, doesn't work. So t equals to negative 2 is not a regular singular point. So applying power series method at t equals to negative 2 will be much harder. Around the regular singular point, t equals to 2, it's gonna be a doable job. Let's go over to an example problem. Again, let's keep a little bit larger font. And here's an example. Here's a general theory. Frobenius method. Instead of plugging in the power series directly, we have additional factor multiplied in there, t minus t0 to the nth power, so that if you slip this one in, then we have n plus r power. And it is possible to identify what r is. And that's the essence of Frobenius method. Let's work it out to an example. I'm not so sure whether I can finish this long problem in a single video. Let's try as much as possible. Here's an example problem. And first, is this a regular singular point? Yes, it will be. Let's see. T equal to 0. We have second power, first power, 0 power with second derivative, first derivative, 0 derivative. We have like that. So if you take appropriate division, divide by 2t squared, and then divided by 2t squared. Then what do you have? We have this simplification. This second power and this t cancel each other out, and what do you get? Second derivative, first derivative, 0 derivative. And look at the denominator. Second power, first power, 0 power, going backward. So this is a regular singular point. So we are ready for Frobenius method. Regular singular point at t equal to 0. So we're going to apply Frobenius method. Not just power series, but n plus r, and then plus r. All right, n plus r power. And then this is a derivative, so n plus r came out and subtract 1 from the power. And do the same thing again. All right, let us put all these into the original equation, but let's do a bit of a preparation. Break up this parenthesis. We can break it later, but let's do it before plugging in. It doesn't matter which one you do first. I decided to break up beforehand. All right, and then I'm going to put in the second derivative and the first derivative, another first derivative here, and then the original here, the original. Ready? Let's go. This is the second derivative right here. That's the first derivative right there, and another first derivative right there, and then for y, just the original, and then that is the power series expression. This is the power series expression of the same differential equation. This one became that. Okay, for the algebra, t squared multiply over here, and then we have n plus r power. T power, first power, so multiply over here in n plus r power. The second power, multiply over here, so n plus r plus 1 power. And this one is the original, so we have n plus r power. So we have this expression here, and experienced students will see that this is going to be a trouble. Why? We have n plus r power, n plus r power, n plus r power. This one is a little bit different. Okay? And by the way, this one came from this factor. T squared and then that. And originally it came from this term. And that. The green part is going to be troublesome part, and then we'll have to do some index shifting. Okay? Let's work out this part, especially the green part, and then I want the same power. Let's do the index shifting. How do we do that? Okay, eventually I want n plus r in there, so if I start from n minus 1 plus r plus 1, then that'll become the same power. So we need n minus 1 everywhere. Basically, this is the index shifting that we're going to end up with. Let's see, let's continue. Let's erase this because we don't need it anymore. Okay, this time green term, and green term. And down here, after index shifting, we got this green series. Does everything look good? Everything is n plus r power. Alright, but additional problem. Instead of n equals to 0, because of that index shifting, we have to start from n equals to 1. That's going to cause a bit of a problem here. When n is equal to 1 or higher, everything makes sense. But when n equals to 0, this green part does not exist. So you have to consider only these three. Well, here we go. When n equals to 0, okay, 0, this green part does not contribute. So plug in n equals to 0 from here, the first series, we get this expression. N is equal to 0, so 0, 0, so we got r and r minus 1. Next, plug in n equals to 0 here again. Okay, and then 0, 0, so C0 and the 3R, and n equals to 0 here, C0, and then this is what we get. Do you notice? This green part does not contribute. Plug in n equals to 0, and then the t to the whatever part is factored out. It doesn't contribute either. So coefficient part, this one, this one, this one, when n equals to 0, we get this. Alright, when n is greater than 1 on the other hand, this green part does contribute, and it's right here. So if you set all those coefficients put together, you get that. And using this one, we can find out the relationship between R and C0. As a matter of fact, excuse me. C0s will just cancel all out. And we can find out what R is from here. C0 is going to be arbitrary. And from here, we can find out the recursive relation. Let's go. First, when n equals to 0, we get R value here. C0s will cancel out, and we get this equation of R. It's a quadratic equation, not very hard. Factor it and solve it, and we get these two R value. R equals 1/2 power or R equals -1 power. I color coded in blue and red because these two different R value will give you two linearly independent solutions of homogeneous equation, y1, y2 basically. Okay, R is 1/2 or R equals to -1. Both apply for this one, and we'll have to do it separately. R equals 1/2, we have one. R equals -1, we have another. Okay, here we go. That's the equation we have, and then okay, and the green part, I no longer need that color coding, so yeah, alright. R equals 1/2 power, alright, plug in R equals 1/2 to this thing, and we get, holy cow, this expression here. And then, alright, R equals to 1/2, as you can see 1/2 isn't there. And then if you do some algebra, you can solve for Cn, and then we end up with this. How do you actually solve it? Some further algebra. I just put in Mathematica command in there. I guess I got really tired of doing all those hand computation. If you do it, you're gonna get this. And then you're gonna plug in numbers repeatedly, starting from n equals to 1, and then you're going to get this kind of recursive relationship. C1 is negative 3/5 C0, and C2 is kind of like that. So we get the rest of the second line from the very first, and then so on and so forth. Is there a pattern for that? According to a textbook author, there was a pattern, so I got like this. But many times, or as a matter of fact, in majority of the times, you don't see this pattern. So what you're gonna end up with is usually here, dot, 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 and then you just move on most of the time. When you're exceptionally lucky, then you can get some definite pattern here, like this. Most of the time, no. What about r equals to negative 1? Again, the same equation here. Plug in r equals to negative 1. And then we get this relation, and you can solve for c of n. And using this mathematical code, if you will. If you use paper and pencil method, it'll take longer, but you can do it. Once you get it, again, plug in numbers. C is C of 1, C of 2, C of 3, you can find out by plugging in n equals 1, 2, 3, 4, and so on. We get O0. We get, okay, first, negative 3 times C0, that's okay. And then plug in n equals to 2, then we get right here, 2 minus 2, so we get 0. So C of 2 is 0. And C3 is, well, there used to be C2, but C2 is 0, so that's 0. And C3 is 0, 0, something times C3 is C4, but that 2 is 0, and so on and so forth. So we're going to get all zeros. So we have a recursive relationship from here. Okay, when r is 1/2, that's going to give you one solution. When r is negative 1, we have another recursive relationship here. This is going to be simpler, all 0, and then we have only 1. And put those two together, we're going to get this solution here. Blue part, when r equals 1/2, we get some complicated expression here because we are kind of lucky and we were able to find out the general term, but in general, you don't have it. So you just put C in here, and then put some recursive relations and dot, 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 and you just stop there. And if necessary, you can run a computer to find out first 1,000 term, and then just go on from there. And for the second case, we have all 0, so we got something simpler. We have only up to the first term, and then the others all disappear. And then this 1/2 part, and then negative 1. Please remember they all came from, let's see, yes, this part. This is 1/2 power, or negative first power, and then you have power series part. Remember, this was the Frobenius method. And then that's what this part and that part is all about. And well, there are some constants flying around, so we could rearrange them and rename them. And I decided to write capital A and capital B for these two solutions, or those two coefficients of these two linearly independent solutions of homogeneous equation, blue and red.